Welcome back to the course. This is Introduction to Azure Networking, and this is Lesson 10, where you'll deploy your first Azure Firewall. By way of introduction, just a quick recap that links to the prerequisites for the course can be found in the Introduction section, and links to the deployment scripts, which are hosted on GitHub, can be found in the Resources section. This lesson comprises two parts. In Part 1, you'll learn how to create a log analytics workspace to store and query firewall logs, how to add subnets to the virtual network for the firewall, how to create public IP addresses for the firewall, how to create the firewall policy, including rule collection groups, rule collections and rules, including destination, NAT, network and application, and how to create the firewall and a diagnostic setting to send firewall logs to the analytics workspace. In Part 2, you'll learn how to update the peering relationships and route tables to use the firewall to govern traffic flow between virtual networks, the VPN and the internet, how to verify connectivity to ensure traffic is flowing through the firewall as expected. We'll provide a recap on the effective routes and effective security rules of the network interfaces so you can understand how routing and filtering works in the updated topology. And finally, we'll provide an introduction to the Kusto query language so you can inspect the firewall logs. Let's review the topology diagram for this lesson. First, let's recap on the resources that we were using from the previous lessons. These include the Hub resource group, its virtual network, along with the virtual network gateway and bastion, the peering relationships to the spoke virtual networks, and the VPN to the data center. We're also reusing the first, second, and third resource groups, their virtual networks, their virtual machines, and their peering relationships to the hub. And lastly, we're also reusing the data center resource group, its virtual network, along with the virtual network gateway, the virtual machine, and the VPN to the hub. In Part 1 of the deployment, in the Hub resource group, we've now also deployed a log analytics workspace to store and query firewall logs, two additional subnets in the virtual network, one for the firewall and one for firewall management, a firewall policy, and two public IP addresses. And finally, we've deployed the firewall itself. In the second part of the deployment, we'll create a route table which will associate to the gateway subnet in the hub, and then we'll adjust the peering and routing configuration of the topology to use the firewall. And now, let's see what this looks like in the Azure portal once everything's been deployed. Here we are in the Hub resource group view. In addition to the existing resources deployed in the previous lessons, we can see that we now also have a firewall, its associated public IP addresses, a firewall policy, a log analytics workspace, and a route table for the gateway subnet. Now it's time for our demonstration, so let's get started. Here we are in Visual Studio Code. We have the first deployment script open and our terminal is ready. As usual, before we execute the script, let's review it so we can understand what it's doing. From the top, we have our variables. For the DNAT firewall rule, we'll need the private IP address of the first virtual machine. So we need its resource group, along with its name and the name of its network interface. We're also going to deploy additional resources into the hub, so we need the name of its resource group along with its location. In the hub, we'll create a log analytics workspace for the firewall logs, so we need its name. For the firewall, we'll create two additional subnets in the virtual network, so we need the name of the virtual network along with the names and address prefixes of the subnets. We'll also create the firewall and its associated resources. We need a name for the firewall and its associated policy, along with the names for the rule collection groups and the rule collections, and the names for the public IP addresses and their associated IP configurations. And lastly, the name of the diagnostic setting used to send the firewall logs to the workspace. Now we have our variables defined, we can begin creating our resources. First, we'll create the log analytics workspace for the firewall logs. For this, we need its name along with its resource group and location. Next, we'll create the two additional subnets for the firewall. For this, we need the name and resource group of the virtual network, along with the names and address prefixes of the subnets. We can then create the public IP addresses for the firewall. For this, we need their names, resource group, and location, along with the skew and allocation method. Notice that for the first address, we're using a query filter for the IP address, which we're storing in a variable. We'll use this later as the destination address when we create the DNAT rule. We can then create the firewall policy. For this, we need its name, resource group, and location, along with the SKU. Just a quick side note here, the SKU of the firewall policy must match the tier of the firewall. In our case, we're going to use the basic tier so that we get all the essential firewall features whilst minimizing the cost associated with our demonstration. Also for the DNAT rule, we need our current public IP address and the private IP address of the first virtual machine. For our IP address, which we'll use as the source address, we can reuse the invoke web request commandlet to the IPinfo API, storing the result in a variable. And for the private IP address of the first virtual machine, which we'll use as the translated address, we can use a show command with the name and resource group of the network interface, along with a query filter for the first private IP address, which we'll also store in a variable. We can then create the rule collection group for the DNAT rules. For this, we need the name and resource group of the firewall policy, along with the name of the rule collection group and an integer value for the priority. Next, we can create the rule collection for the DNAT rules, and notice that in the same command, we can also create the first DNAT rule itself. For this, we need the name and resource group of the firewall policy, the name of the rule collection group, and several other parameters. These include the name of the rule collection and an integer value for its priority, the name and action of the rule, the source address, in this case our current public IP address, the destination address, in this case the public IP address associated with the firewall, the IP protocol and destination port, in this case TCP and 22, the default for SSH, the translated address, in this case the private IP address of the first virtual machine, and finally the translated port, in this case 22, again the default for SSH. We can then create the rule collection group for the network rules. For this, we need the name and resource group of the firewall policy, along with the name of the rule collection group and an integer value for the priority. Next, we can create the rule collection for the network rules, and again notice that we can also create the first network rule at the same time. For this, we need the name and resource group of the firewall policy, the name of the rule collection group, and several other parameters, including the name of the rule collection and an integer value for its priority, the name, type, and action of the rule, the source address, in this case any, represented by an asterisk, the destination address, also any, represented by an asterisk, the IP protocols, which we'll set to any, this includes TCP, UDP, and ICMP, the destination ports, in this case we want all 65,535 ports, apart from port 80 and port 443, for which we'll create application rules. Despite the IP protocols being set to any, which includes ICMP, this traffic will not be permitted by this rule since we've restricted the destination ports. We'll add another rule to the existing rule collection to permit this traffic. For this, we need the name and resource group of the firewall policy, the names of the rule collection group and the rule collection, the name and type of the rule, the source address, in this case any, the destination address, in this case also any, the IP protocols, in this case ICMP, and the destination ports, in this case also any. Next, we can create the rule collection group for the application rules. For this, we need the name and resource group of the firewall policy, along with the name of the rule collection group and an integer value for the priority. We can then create the rule collection for the application rules, along with the first application rule. For this, we need the name and resource group of the firewall policy, the name of the rule collection group, and several other parameters. These include the name of the rule collection and an integer value for its priority, the name, type, and action of the rule, the source address, in this case any, the target FQDNs, in this case also any, and the protocols, in this case HTTP on port 80 and HTTPS on port 443. Next, we can create the firewall. For this, we need its name, resource group, and location, along with several other parameters. These include the SKU and tier, the name of the public IP configuration for inbound and outbound traffic and its associated public IP address, the name of the public IP configuration for management and its associated public IP address, the name of the firewall policy, and the name of the virtual network. Notice here that we're using a query filter for the resource ID, which we're then storing in a variable. We'll use this when we create the diagnostic setting to send the firewall logs to the analytics workspace. For the diagnostic setting, we need its name and resource group, along with the resource ID of the firewall. We also need to specify the scope of the logs, which we can do by referring to a JSON file, which we'll review in a moment. And we also need to specify the name of the log analytics workspace and the parameter to send the logs to resource-specific tables within the workspace. And finally, let's review the in-scope firewall logs. Here we have a simple JSON structure, which specifies the log categories and whether they're enabled. We're including the categories for network rules, application rules, NAT rules, and threat intelligence. We can now execute the first script, which will deploy the resources. Here we are again, back in Visual Studio Code, this time with our terminal window maximized. Just a quick side note here. In the diagnostic setting, we specified the in-scope logs using an external JSON file. We must therefore execute the script from within the directory containing the JSON file, otherwise the deployment will not complete successfully. Let's execute the first script and observe the deployment. If you're following along, in a moment you may wish to pause the video here until the deployment is complete on your side. Just a quick side note here. If you're following along, don't be alarmed if you think the deployment script has hung when it comes to creating the firewall. This can take anywhere from 10 to 15 minutes to complete, and we need this to be in a succeeded state before we can configure the diagnostic setting, so please be patient. Now our first deployment is complete, let's change over to the Azure portal to review our resources. Here we are in the Azure portal in the Hub Resource Group view. Let's review the virtual network. Under Settings, we'll review the subnets. Here we can see that we have two additional subnets for the firewall. The firewall subnet is allocated 10.0.2/24, and the firewall management subnet is allocated 10.0.3/24. Let's go back into the resource group view, and let's review the firewall. Under Essentials, we can see the SKU, the subnet in the Hub virtual network, the public IP address used for inbound and outbound traffic, the private IP address of the firewall, the management subnet in the Hub virtual network, the public IP address used for management, and the firewall policy. Note that we can also see a summary of the rules. That threat intelligence is enabled in alert mode, and that in the basic SKU, the TLS inspection and intrusion detection and prevention features are not supported. If we select the firewall policy, under Settings, we can review the rule collections. Here we can see the structure of the rule collection groups and rule collections that we specified in our deployment script. If we review the rule collection for the DNAT rules, we can see the rule that allows inbound SSH access to the first virtual machine. If we review the rule collection for the network rules, we can see the rules that allow all TCP and UDP traffic on all ports except 80 and 443, along with all ICMP traffic. And if we review the rule collection for the application rules, we can see the rule that allows HTTP traffic on port 80 and HTTPS traffic on port 443. Also under Settings, if we review the private IP ranges, here we can see that, by default, when processing network rules, the firewall will apply source network address translation to all traffic except for the IP address prefixes included in RFC 1918. Just a quick side note here, when processing application rules, the firewall will always perform source network address translation, regardless of whether the application is hosted within the virtual network, out on the internet, or on the other end of a VPN connection. If we go back to the firewall, Under Settings, we can review the public IP configuration. And here we can see the IP configuration for inbound and outbound traffic and its associated public IP address. Under Monitoring, we can see the diagnostic settings. If we edit the setting, we can see the log categories that were enabled during the deployment and that these are being sent to the Log Analytics workspace in resource-specific tables. Now that we've reviewed our resource deployment, let's return to Visual Studio Code to review the second deployment script. Here we are back in Visual Studio Code. We have the second deployment script open and our terminal is ready. As usual, before we execute the script, let's review it so we can understand what it's doing. From the top, we have our variables. In the hub, we're going to be creating new resources and adjusting the configuration of existing resources. So we need the name and location of its resource group, along with the name of the virtual network, its gateway subnet, the route table we'll associate to the gateway subnet, and the name of the firewall. The rest of our variables will be dynamically generated throughout the remainder of the deployment script. We're going to be updating the routing configuration within the topology, so we'll need the private IP address of the firewall. We can retrieve this using a show command, along with the name and resource group of the firewall, along with a query filter for the private IP address of the first IP configuration, which we'll store in a variable. We're also going to be updating the configuration of the peering relationships in the hub. We can retrieve these using a list command, along with the name and resource group of the virtual network. We'll format the output using JSON, which we'll then convert into an object, which we'll store in a variable. We can now use our familiar for each loop to iterate over the peering relationships in the hub to remove the configuration parameter for allowing gateway transit. We'll obtain the name and resource ID of the current peering in each iteration, and we'll then update the peering by specifying its resource ID along with the parameter to remove the allow gateway transit configuration. Next, we'll create a route table for the gateway subnet. To do this, we just need its name, resource group, and location. We can then associate the route table to the gateway subnet. To do this, we need the name and resource group of the virtual network, along with the name of the subnet and the name of the route table. We have 3 spoke virtual networks, which means we need to repeat the same configuration multiple times. In Lesson 8, we learned how to create our own simple data structures using an array. Don't worry if you can't remember the syntax for this, we'll recap on it here. We'll create the array using the @ symbol and a pair of parentheses, and inside of the parentheses we'll add the items to the array, in our case the index numbers of the spoke virtual networks. We'll then use another for each loop to iterate over the array. First, we'll dynamically create some additional variables. In each spoke, we're going to be adjusting the configuration of existing resources, so we need the name of its resource group, along with the name and address prefix of its virtual network, the name of its subnet, and its associated route table. Like in the hub, we're going to be updating the configuration of the peering relationships, this time from the spoke. We'll reuse the same method to retrieve the peering relationships via a list command, providing the name and resource group of the virtual network, formatting the output using JSON, converting the output into an object, and storing it in a variable. We'll then use a nested for each loop to iterate over the spoke peering relationships to remove the configuration parameter for using remote gateways. We'll again obtain the name and resource ID of the current peering in each iteration. We'll update the peering by specifying its resource ID, along with the parameter to remove the use of remote gateways. Next, we also want to adjust the routing configuration for the spoke virtual network. In Lesson 8, we populated each route table with a pair of user-defined routes to the other spokes in the topology with the next top type of virtual network gateway. These routes are now redundant and can be removed. We'll obtain the routes from the route table, again using a list command, along with the name and resource group of the route table, formatting the output as JSON, converting it to an object, and storing it in a variable. We'll then iterate over the routes stored in the variable using another nested for each loop, and in each iteration we'll obtain the name and resource ID of the route. We'll then delete the route by providing its resource ID. We now want to ensure we have symmetric routing in our updated topology. To do this, we must first populate the route table associated to the gateway subnet in the hub with a user-defined route to the spoke virtual network via the firewall. We can do this by providing the name and resource group of the route table in the hub, along with the name and address prefix of the spoke virtual network, the next hop type of virtual appliance, and the next hop IP address of the firewall. And then, to complete the routing, we must also override the default quad 0 system route in the spoke, which has a next hop type of internet, with a user-defined route which matches the address prefix, but instead routes the traffic via the firewall. We can do this by providing the name and resource group of the route table in the spoke, along with the name and address prefix of the default route, the next hop type of virtual appliance, and the next hop IP address of the firewall. We can now execute the script, which will deploy the resources. Here we are again, back in Visual Studio Code, this time with our terminal window maximized. Let's execute the second script and observe the deployment. If you're following along, in a moment you may wish to pause the video here until the deployment is complete on your side. Now our second deployment is complete, let's change over to the Azure portal to review our resources. Here we are back in the Azure portal in the Hub Resource Group view. Let's review the virtual network. Under Settings, we'll review the subnets. Here we can see that the gateway subnet now has a route table associated. Also under Settings, we'll review the peerings. If we review the peering to the first virtual network, we can see that the hub virtual network is allowed to access the first virtual network, but that we're no longer allowing the gateway in the hub to forward traffic to the first virtual network. If we were to review the peering relationships to the second and third virtual networks, we would see a matching configuration. Why don't you try this for yourself? If we go back to the resource group view, and now let's review the route table for the gateway subnet. Here we can see that we have routes to the first, second and third virtual networks, with the next hop IP address being the firewall. Let's go back to the resource group view. And now let's review the public IP address of the firewall. Here we can see the IP address that's been allocated. We'll copy this to our clipboard as we'll need it shortly to be able to connect to the first virtual machine over the internet. Let's now change over to the first resource group view. And again, let's review the virtual network. Under Settings, we'll review the peerings. And here we can see the peering to the hub. If we review the peering, we can see that the first virtual network is allowed to access the hub virtual network. The first virtual network is also allowed to receive forwarded traffic from the hub virtual network. But notice that we're no longer allowed to use the remote gateway in the hub virtual network. If we were to review the peering relationships for the second and third virtual networks, we would see a matching configuration. Why don't you try this for yourself? Let's go back to the resource group view. And let's review the route table for the first subnet. Recall, in Lesson 8, we had routes to the second and third virtual networks. This has now been replaced with a quad 0 default route, with the next hop IP address being the firewall. If we were to review the route tables for the subnets in the second and third virtual networks, we would see a matching configuration. Why don't you try this for yourself? Let's now validate connectivity over the updated topology. Here we are, back in Visual Studio Code, with our terminal window maximized. Let's test the DNAT rule on the firewall by establishing a connection to the first virtual machine. Here we can see we've successfully connected to the first virtual machine through the firewall. From the first virtual machine, let's validate connectivity to the second virtual machine. Here we can see we've received a response to each of our requests. Let's now establish a connection to the second virtual machine. Here we can see we've successfully connected to the second virtual machine. While we're here, let's validate the public IP address that is now used to access resources on the internet. Here we can see that this is the same IP address that we used to connect to the first virtual machine. This verifies that traffic sourced from within the virtual network destined for the internet is being successfully routed via the firewall. From the second virtual machine, let's validate connectivity to the third virtual machine. Here we can see we've received a response to each of our requests. Let's now establish a connection to the third virtual machine. Here we can see we've successfully connected to the third virtual machine. From the third virtual machine, let's validate connectivity to the virtual machine in the data center. Here we can see we've received a response to each of our requests. And finally, let's establish a connection to the virtual machine in the data center. Here we can see we've successfully connected to the data center virtual machine. Let's review the effective routes and effective security rules so we can understand how our new topology works. Here we are back in the Azure portal in the first resource group view. Let's go into the network interface of the first virtual machine and view the effective routes. Let's order the routes by address prefix. Here we can see that the quad 0 system route with the next hop of internet has been marked as invalid. This is because we now have a matching quad 0 user-defined route with the next hop to the firewall IP address, which overrides the system route. We also have a 10.0/16 system route with the next hop type of VNet peering. This is the route to the hub virtual network. And finally, we have a 10.1/16 system route with the next hop type of virtual network. If we were to review the effective routes of the network interfaces for the second and third virtual machines, we would also see that the default system route to the internet is invalidated by a user-defined default route to the firewall, a matching route to the hub with the next hop type of virtual network peering, and a virtual network route for the respective spoke. Why don't you try this for yourself? Let's now review the effective security rules. Here we are in Network Watcher. Let's review the effective security rules. We'll select the first resource group, and then the first virtual machine, and then the network security group associated to the subnet. Here we can see the inbound and outbound rules, and we can observe that the virtual network tag now only has one prefix. If we select the virtual network tag, we can see that it now includes the quad 0 prefix, which matches all traffic. If we were to inspect the effective security rules of the network interfaces of the second and third virtual machines, we would see a matching prefix in the virtual network tag. Why don't you try this for yourself? And finally, let's review the firewall logs. Here we are in the Log Analytics workspace. Let's review the logs. We'll minimize the resource blade to give us some more space. In the Queries hub, we'll search for firewall. And under all queries, we'll choose security. We'll then choose all firewall decisions. Let's load this query to the editor. And again, we'll minimize the queries blade to give us some more space. This isn't the first time we've seen a query like this. Recall in lesson 3, we reviewed the network security group flow logs. This is a similar query, and the syntax is known as the Kusto query language. Don't worry if this looks a bit confusing, we'll go through it step by step. On line 3, the query begins with the table in the workspace which contains the logs for network rules. On line 4, the query uses the union operator to add the tables for application rules, DNAT rules, threat intelligence, and intrusion detection and prevention. Just a quick side note here, we're using the basic firewall SKU which doesn't support intrusion detection and prevention. We can remove this table from the query. On line 5, the query uses the take operator and the integer value of 100. This simply means return a sample of up to 100 rows from the tables. Also note that at the top of the query, to the right of the blue Run button, we can select a time range. This defaults to the last 24 hours, which is fine for our purposes. Let's run the query. Here we can see that we've returned 33 results. By default, the results are usually shown in a time-generated column in UTC. To make parsing the logs easier, you may want to change this to a local time zone. Also note, a large number of columns have been returned, many of which are not useful to us. When we validated connectivity over the new topology, we started by establishing a connection to the first virtual machine over the internet. Let's search the logs to identify this connection. First, we'll remove the take operator on line 5. For our purposes, we can just comment this out using 2 forward slashes. Next, we'll extend this query onto line 6 using a pipe. We'll then add the where operator, followed by selecting the destination IP column. Then the equality operator, and inside of double quotes, we'll select the public IP address of the firewall. We'll then add the AND operator, followed by selecting the action column. Then the not equals operator, and again, inside of double quotes, we'll select the deny action. Before we run the query, let's remove some of the columns that we aren't interested in. We'll again extend the query onto line 7 using a pipe. We'll then add the project operator, followed by selecting the columns that we're interested in. Let's include the time generated, the source IP, the destination IP, the protocol, the destination port, the translated IP, the translated port, and the rule. Let's now run the query. And here we can see that we've narrowed down the results to 2 records. The traffic's arrived on the public IP address of the firewall on TCP port 22. It's been translated to the first virtual machine, also on port 22, and it's been permitted by the rule to allow SSH. Next, let's amend the query to try and identify the connection from the first virtual machine to the second virtual machine. On line 6, we'll change the destination IP column to the source IP column. And we'll change the IP address to be the private IP address of the first virtual machine. We'll then replace the action not equal to deny statement with the destination port equal to 22 statement. And on line 7, we'll remove the translated IP and translated port columns and instead add the action column. Let's now run the query. And here we can see that we've also narrowed down the results to 2 records. The traffic has originated from the first virtual machine, destined for the second virtual machine, on TCP port 22, and it's been permitted by the rule to allow network traffic. Next, let's amend the query to try and identify the connection from the second virtual machine to the internet. On line 6, we'll change the source IP to the private IP address of the second virtual machine. We'll then replace the destination port equal to 22 statement with the fqdn equal to ipinfo.io statement. And on line 7, we'll replace the destination IP column with the fqdn column. Let's again run the query. And again, here we can see that we've narrowed down the results to 2 records. The traffic has originated from the second virtual machine, destined to the ipinfo fqdn on HTTPS port 443, and it's been permitted by the rule to allow application traffic. This was just a very simple introduction to the Kusto query language, which is an incredibly powerful tool to explore your data and discover patterns, identify anomalies and outliers, create statistical modeling, and more. Why don't you experiment with further queries in your own environment? That concludes not only this lesson, but the first 10 lessons in this introductory course. I hope to add future lessons, either as bonus content to this course or as another standalone course. Either way, I hope you found these lessons useful, and I look forward to seeing you again next time. But for now, this has been Introduction to Azure Networking. Thanks for watching.